So here's the second part of this video about these fundamental limits. And this is the other one that goes into thinking about derivatives of sine and cosine, for example. But again, it's worth thinking about on its own. And so the idea here is, if we know what sine does for small angles, what does cosine do for small angles? Okay. And the thing is that you might think it's just really easy to say, look, we know cosine of 0 equals 1, and it's a continuous function, so cosine of theta should be approximately 1 if theta is small. And that's a true fact. It's just that we can say more. Okay, they're not equal, and it's worthwhile to consider how different they are. And for various things, it's really quite crucial to consider it. Okay, so in other words, cosine theta minus 1 is approximately 0. Now, there's various different versions of approximately 0. That's saying that this is a small number. But how small, right? If theta is like 0.1 radians, is this more like 0.1? Is it more like 0.01? 0.001? Is it even not even as small as 0.1? Is it like 0.5? Just how small is small, okay? And so once again, comparison by ratios comes to the rescue. What we can do is we can say 1 minus cosine theta. Now that's going to be the positive quantity. Here I wrote it this way, but that's going to be negative. That's a little bit annoying. So, and it's going to be really important that that's going to be definitely positive, okay? But how small is it? So we're going to take 1 minus cosine theta. Just kidding, okay. And we're going to compare it to theta itself. So if the limit of this guy ends up being super small, that's saying that 1 minus cosine theta is not just small, it's qualitatively smaller than theta itself. If this limit were something different, it would be say something different. But in fact, the claim is that this actually goes to 0 as theta goes to 0. Okay. So it's actually a little bit more subtle statement than the other one. It's saying that when I take cosine theta, I compare it to 1 by subtraction. We know that's going to be a small quantity. And it's actually really small, because even when I divide it by theta and compare it to theta, I still get a small number. All right, so we want to think of this as saying that for small angles, theta, it's that cosine theta, I kind of want that in math mode, don't I? Is very close to 1. So much so that if I look at its difference from 1, and then I even divide by this known small quantity, I actually still get something that's 0. Okay, so what does that say in terms of the picture? Okay, well, cosine, of course, is just OC here, because we're on the unit circle. Again, the angle is here, but we're also going to think of it as the arc length from A to P. The cosine is just the x-coordinate of the point P, so that's marked here, like here it's 0.853. 1 minus cosine, conveniently, is just exactly AC right here. So we're just basically analyzing this distance and claiming that it gets really, really small in a certain precise sense when P is brought down. Okay, let's convince ourselves that it does get small. Yeah, it's getting pretty small. And notice it disappears from view quite a bit before I can't tell the difference between P and A. Remember, the distance between P and A, whether it be this vertical distance or the straight line distance or the arc length, those are basically all becoming the same thing. That was from the first video. That's the small number theta. And here that's like 0.161, right? You can see this number, the sine, and this are very similar to each other. And right about here, they start being indistinguishable from each other. That's moderately small, but boy, this quantity, it's decided to call it J, is really, really small. And so what we're saying is that this is not misleading, that this quantity J, even if I divided it by this guy, it's still going, that quotient is still going to 0. So let's zoom in a little more, and then I'm going to zoom back out to illustrate the geometry here. Oh man, yeah, okay. When P and C are they're still noticeably far apart at this scale, I cannot tell the difference between these two horizontal positions. And wow, J is almost so small that it's going off the charts in terms of 3 decimal places. If I took it down a little bit further, it's not even going to be able to tell the difference unless it went to 4 decimal places. Okay, so we just want to make sure, we're just trying to convince ourselves that that's accurate, that AC is really, really small, even when compared to the small quantity that is theta, this arc length. Okay, so let's zoom out a little bit. so we can get the geometry correct. This is where this angle beta is going to come in. Uh-oh, let's see. Can I move that? Okay. It's really, no, okay, there we go. Okay. We're going to use this angle because we're going to use this right triangle APC here. Okay. So I want to show that AC is small compared to this arc length. So let's see. It turns out to be really nice to look at AC in this right triangle. Okay. And so AC, that's my 1 minus cosine theta. Okay. And remember the arc length, arc from A to P, that's just equal to theta, so I'm just going to call it theta. It's a nice one-letter thing. Okay. And then I'm also going to use the straight line distance AP. Okay. And all I'm going to use about AP is that it is definitely slightly less than theta, than the arc distance. That's the straight line distance. This is the circle distance. That's going to be less. Okay? Alrighty. And then the only other thing we need to know is that AC in that picture, I'll come back to the picture in a second, is AP sine beta. Okay, let's go back to the picture. Okay. AC is what we're trying to analyze. That's that 1 minus cosine quantity. And we've got a right triangle. AP is the hypotenuse. This is the opposite. So opposite is hypotenuse times sine. Just a restatement of the classic definition of sine, where we're accessing this angle beta. Okay. And so, alrighty. And so AC is definitely a positive number. Nothing here is going to go negative. And that is less than theta sine beta. So just using the fact that AP is less than theta. Oh, sine beta, my bad. Okay. Alrighty. So now the quotient that we're trying to analyze is AC over theta. That's this thing that does this nice comparison of two small quantities. And just dividing this inequality here by theta on both sides and noting that everything's still positive. Okay. Now to be technical, what I'm going to quote next is called the Squeeze Theorem, but we don't have to use it in any complicated way. I want to show that this gets really, really small. In fact, it goes to 0 when theta goes to 0. We know it can't possibly go negative. If I can show that this goes to 0 when theta goes to 0, this is going to be squeezed in between and also has to go to 0. So let's look at this. It's the sine of beta. Let's look at what beta does, right? As p goes down here, we know that this straight line PA becomes very close to vertical. And beta is just the angle between that and an actual honest-to-God vertical. Let's zoom in. Look at what beta is now. It's like 5 degrees, 4 degrees, 3 degrees. It's tiny. Oh, and it's okay that it's registering beta in degrees because all I'm using about beta is just that it's small. So if you're wondering, like, wait, I thought you said you had to be in radians. It doesn't really matter. Probably be more elegant if I had it register beta in radians, but I didn't want to worry about it. Okay. As we get closer and closer, that angle is going very, very, very small. And so sine beta is going to 0. Okay. So sine of beta is going to 0. Therefore, this is also going to 0. And so the limit of AC, after all, was just our geometric way of saying 1 minus cosine theta over theta equals 0. Oh, and that's in the limit that we were showing in the picture as theta goes to 0. Okay, so that's how I would talk about that. Not absolutely completely rigorous in every step, but you can totally make it rigorous pretty easily.